the last video that we did was on ionic bonds, and it was just metal to nonmetal. And that's what we're going to do at the beginning of this one. This is ionic bonding 2. We are going to learn how to name binary compounds. That means two-element compounds. So obviously, we're going to use these. These are metals, okay? So a binary compound is when a metal is hooked to a nonmetal. Okay, they are called binary compounds. And there's some tough ones to name, but here's what we're going to do first. We're going to go over electron dot of a binary compound, then we're going to name it. So first thing, we're going to go magnesium. And magnesium is in group 2, which means it has 2 valence electrons, so it must lose 2 if it's going to go into a binary compound. So here, we're going to go, there's 1 electron, there's 2 electrons for magnesium. Now, plus oxygen. Oxygen is in group 16, which means it's got 6 valence electrons. There's your S2, P1, P2, P3, P4. So now I have magnesium wants to lose 2, and oh look, oxygen wants to gain 2. This should be perfect. So we go Mg. It must lose those 2 electrons, so it turns into this, plus 2. Then, remember, if it's a metal to nonmetal, chances are there's a total transfer. And to show total transfer, I use brackets. So we got brackets, brackets, and then we put the element in there, that's oxygen. And before we put the electrons around, remember it needs a stable octet. The negative ion needs a stable octet. Before we put those electrons around there, we have to see what the oxidation state or charge is of oxygen. And oxygen has this charge, minus 2. So look, plus 2 minus 2 equals 0. I don't have to crisscross. If the 2 charges equal 0, you don't have to crisscross. So that's perfect. Now let's plug in the electrons. So we have 2 electrons there, but we're going to put in these first. So we have 1, 2, 3, 4, 5, 6. And then we have the 2 from magnesium. 1 goes there, and 1 goes there. So there's your stable octet. Let's get this out of here so it doesn't. So here's your stable octet. It's a perfect. Magnesium wants to lose 2, oxygen wants to gain 2, that equals 0, and that's perfect. Now, how do you name it? The naming of a binary compound is kind of easy at first. If the metal, now listen to me, I want everybody, everybody, listen to me. If the metal only has 1 oxidation state, look, if this metal only has 1 oxidation state, like lithium has a plus 1, or calcium has a plus 2, or aluminum has a plus 3, if the metal only has 1 charge, you just name it. But if the metal has more than 1 charge, like copper is a plus 1 or plus 2, gold is a plus 1 or plus 3, so if the metal has more than 1 charge, you got to name it differently. But for now, what we're talking about, we're talking about magnesium that only has 1 charge. So the name of this would be the name of the first element, magnesium, and then the second element, just add "ide." So that's magnesium oxide. That is magnesium oxide. Remember, magnesium only has 1 charge. That's how you name it. Okay, so watch. So what we're going to do now is we're going to do a different one, okay? We are going to use this one. We're going to use iron. Now, iron can be a +2 or +3. That means iron can lose 2 electrons or iron can lose 3 electrons. And we're going to hook that with fluorine. And fluorine's charge is a -1. So here's the question. How do you tell which charge iron is going to use? Well, watch this, okay? So we're going to use iron. But here is what they would give you. It would be iron So what if they gave you iron Roman numeral 3 fluoride? What the heck does that Roman numeral mean? Whenever you see a Roman numeral next to the metal, that means the charge or the oxidation state. It doesn't mean take the third charge down. It means that's a +3. So whatever the Roman numeral is, that is the charge. So if I were to draw this, I would go Fe, Roman numeral 3 means a +3, and then fluoride would be fluorine, F, and fluorine has a -1. So look, Fe +3, F -1, that doesn't equal 0. That's +3 and a -1. So how do we make it equal 0? How do we make the charges equal 0? Crisscross and drop the sign. So that 1 goes there, but we know we got one of them. So we're going to take that 3 and put it right there. So that is FeF3. That is iron Roman numeral 3 fluoride. Okay? Iron Roman numeral 3 fluoride. So if you see a Roman numeral, that means the charge. Let's do another one. Let's do gold, Roman numeral 1, oxide. So, gold is Au. The Roman numeral 1 means +1. Oxygen is O, and the charge on oxygen is a -2. So if you look at that, +1 and -2, that doesn't equal 0. So how do I do it? Crisscross and drop the sign. So I know I've got 1 oxygen, so I don't have to put the 1 there, but I'm going to put a 2 right there. So that is gold, Roman numeral 1, oxide. Gold, Roman numeral 1, oxide. Okay? The other way to name, where I give you the compound and you got to name it, that's a lot harder. So watch. If I were to give you this, CuCl2, and I said name that, most of my students would go, oh, okay, that's copper chloride. That's wrong. The reason that would be wrong come on. The reason just to name copper chloride would be wrong is look at copper. Copper can have a +1 or a +2 charge. You got to tell which charge is being used. All right? If the element has more than 1 oxidation state, you got to do a Roman numeral. All right? Most of the transition elements have that. So if the element doesn't have more than 1 oxidation state, like silver, silver only has a +1. You don't have to say silver Roman numeral 1. because it's only got one charge. But we got to do something with that copper. Okay? So, look. We know copper can be a +1 or a +2. We have to figure out which one is being used. Well, chlorine is this. Chlorine is a -1. And there are 2 chlorines. So, if there are 2 chlorines with a -1 each, copper must be a +2. So it would be +2. So now you know the name would be this. Copper, Roman numeral 2 chloride. Remember, if you just write copper chloride, it's wrong. Okay, so let's do another one. Okay, so what we're going to do is let's pick barium and nitrogen. We're going to pick barium and nitrogen. So now, question, does the metal have more than one oxidation state? There's barium. Barium's charge is only a +2. Do I need a Roman numeral? No, because it only has one charge. So let's put this together electron dot wise and name it. So if it only has one charge, we can name it right now. It's got to be barium nitride. But let's do the whole thing. All right, so we have Ba. It's got 2 valence electrons plus N. N is in group 15, got 5. So we got pair, single, single, single. So that's what that's going to look like. So now, when we put them together, barium must lose 2. So we go Ba plus 2. Then remember, since this is a metal to nonmetal, there's a total transfer, and to show total transfer, we need brackets. And then we put the negative ion in N, oops, sorry. We put N in there, and then we find out its oxidation state. N's oxidation state is a -3. So watch, that's a +2, that's a -3. So that doesn't equal 0. So crisscross and drop the sign. So that 2 goes here, and that 3 goes here. Now we can plug in the electrons. Well, we have 5 from nitrogen. 1, 2, 3, 4, 5. And then barium wants to give up 2, but remember this. There are 3 bariums, each giving up 2 for a total of 6. So we have a +6, which means it wants to give up a total of 6. Now we have 1 nitrogen wants 3, but we have 2 nitrogens. So 2 nitrogens, each wanting 3, will be a -6. So we have a +6 and a -6. That equals 0. So now we just plug in X, X, X. And we have a stable octet. Name. Since barium only has 1 oxidation state, you just name it. So this would be barium nitride. So that's how you name binary compounds. If the metal only has 1 charge, like group 1, group 2 metals, or aluminum, or silver, if the metal only has 1 charge, you just name it. But if the metal has more than 1 charge, like cobalt is +2 +3, Iron plus 2 plus 3. Manganese is crazy. Plus 2 plus 3 plus 4 plus 7. Gold plus 1 plus 3. If the metal has more than one charge, when you name it, you have to name it with a Roman numeral, whichever one you use. Okay? So that's naming binary compounds. So what I was saying in the first ionic compound video was there are 3 types of ionic bonds. That's just the first one. Metal to nonmetal for binary compounds. The second type of ionic compound deals with this. It is a metal not hooked to a nonmetal. It is a metal hooked to a polyatomic ion. Now, what's a polyatomic ion? Well, let's check it out. This is table E, and this is selected polyatomic ions. Selected polyatomic ions. Now, a polyatomic ion we'll write down is a group of elements that can't be broken down, that acts like a single element and has one charge. All right? So, all these, they can never be broken down. And they usually end in this, 8 or ite. Most of the polyatomic ions end in 8 or ite. Some don't, but most do. And remember, they act like a single element. They can't be broken down. So they're not too bad. So this is table E. And what I do is I tell my students, if they see a polyatomic ion, put it in parentheses. It's easier to name that way. So let's write down about polyatomic ions before we do a few. So, for number 1 about polyatomic ions, they act like a single element. So they act like a single element, and you can't break them down. You can't break them apart. That's the big one. All right, that's number 1. Number 2. Number 2 is easy. They only have one oxidation state. Remember, I don't like saying oxidation state. It takes too long, so I just say charge. So, that is number 2. Number 3. Most of the polyatomic ions end in 8 or ite. Those are good ones. Most end in 8 or ite. That's number 3. Number 4. There are exceptions that don't end in 8 or ite, and the ones we use the most. Letter A, OH minus. We use that a lot. That's hydroxide. So That's hydroxide. Another one is this, H3O plus, and that's hydronium. NH4 plus, that's ammonium. And we'll just do one more. Cyanide. That's Cn minus. Okay, so these are the exceptions. There's a couple more, but the most important exception for us is this one. OH minus is hydroxide. So most end in ate or ite except these guys right here. And it's real easy to put together a metal plus a polyatomic ion. You just name them both. So here we go. So let's put together calcium and phosphate. Now, when I put together these two things, you know calcium, it's in group 2. It only has one charge, which is a +2. So you don't need a Roman numeral. But what's this phosphate thing? Is it an element? No, it's not an element because of this. It ends in ATE. That's the hint. If you see something that ends in ATE, it's a polyatomic ion, so you have to look it up on the table E. So, calcium, Ca. And calcium's in group 2, like I said, it must lose 2 electrons, so this is a +2. And then phosphate, remember I said if you detect a polyatomic ion, just put it in parentheses, it's easier to name. So, looks like this. And inside would be PO4, and then outside the parentheses, the charge is a -3. So if you look at this thing, it's Ca +2 PO4 -3. A +2 and a -3, they do not equal 0. Crisscross, drop the charges. So that 3 goes there, and that 2 goes there. Now, how do you name it? Would this be calcium Roman numeral 2 phosphate? No, because calcium only has one charge when you look at it on the periodic table. So the name of this is simply the name. It's calcium phosphate. That's it. No Roman numeral because calcium only has one charge. So it's if the metal only has one charge, you name the metal, and then you name the polyatomic ion, and you're done. All right, let's do a couple more. This time I'm going to give you the name, you got to build it. So the name of this thing is ammonium sulfite. So ammonium doesn't sound like an element to me, so you have to look on the polyatomic ion chart. And this is not just sulfur because look, it ends in ITE. So that's a polyatomic ion there and a polyatomic ion there. So you got to look them up. So ammonium is this, NH4 plus. That means NH4 is a +1. Sulfite is this, SO3 -2. So you're looking at that and you're going, well, that +1 and that -2, that doesn't equal 0. So what you have to do is this, parenthesis, parenthesis, and now you just crisscross. If it doesn't equal 0, crisscross. So now that 2 goes right there. So that is ammonium sulfite. Okay? 2 more and then we're done with this. All right. The next one that we are going to put together is this. Iron, Roman numeral 2. Iron, Roman numeral 2, hydrogen carbonate. You're going, whoa. Well, I know what iron, Roman numeral 2 means. So iron is Fe. Roman numeral 2, remember, whatever the Roman numeral is, that's the charge. So it's iron plus 2. But what the heck is that hydrogen carbonate? Well, let's check it out. Hydrogen carbonate. Let's see. There it is right there. Hydrogen carbonate. Right there. So now, look what hydrogen carbonate is. HCO3 minus 1. So that's what you put down. HCO3 minus 1. So you go, parentheses, remember, HCO3 minus 1. So now if you look at that, do the charges equal 0? No, this is a plus 2, that's a minus 1. If the charges don't equal 0, crisscross. So that 1 is a given, so I put a 2 over here, and that is the name of that. Iron, Roman numeral 2, hydrogen carbonate, that's what it would look like. One more. All right, the next one we're going to put together is this. Aluminum. Aluminum nitrate. So, question, how come the metal aluminum doesn't have a Roman numeral after it? Because aluminum only has 1 charge, okay? How do you know that that's just not nitrogen? Because it ends in ATE. So now let's put this together. Al, look up the oxidation state or charge, it is a plus 3. All right, nitrate. You look up nitrate and nitrate, it's right here. Nitrate is NO3 minus 1. So that's what we're going to use. So now, parentheses, NO3 minus 1. Now look at that. Does the plus 3 and a minus 1 equal 0? No. So you have to crisscross. So it would be that 3 will go right there. So the correct formula for aluminum nitrate is AlNO33. Okay, so now we've gone over 2 types of ionic compounds. Metal to nonmetal, which is called a binary compound, and then metal to polyatomic ion. They're both ionic compounds, and if the ionic compound doesn't contain a transition metal, chances are it's going to look like salt. It's going to be a crystal, and it's going to be clear like this. If the does contain a transition metal, if the ionic compound does contain a transition metal, then it's going to look like this. It's going to be colored because it has a transition metal in it. So the final type of ionic compound, we've had metal, nonmetal, binary compounds, we've had metal polyatomic ion. This is the final type, and it's called metallic hydride. So metallic hydride, well, it's got a metal in it, it's got hydrogen. So here's the deal. Number one, so when hydrogen rips off a that's what it does. When hydrogen rips off a group 1 or group 2 metal. Can't rip off any other metals. Just group 1 or group 2. Okay? And the deal is, if hydrogen rips off a group 1 or group 2, that's the big deal. So if hydrogen rips off a group 1 or group 2 metal, the charge or the oxidation state of hydrogen must be a -1. And I'm just going to give you 2 examples. So number 3, here are your 2 examples. Let's go with sodium, Na, that's in group 1, so that's a +1. And if it's hooked with hydrogen, H -1. So Na+1, H -1. Don't forget, some of my students put Na+1, H +1. You can't have 2 positives together because that means they both want to lose. So Na+1, H -1, the name would be sodium hydride. So that's one example. And now here's your other example. Let's take a group 2 metal. Ca+2. We're going to hook it up with hydrogen. And remember, that doesn't work. You didn't have to crisscross this one because +1 -1, that equals 0. But +2 -1 doesn't equal 0. Crisscross. Going to be a 2 there. So it's CaH2, and the name is calcium hydride. There we go. So, the 3 types of ionic bonds: metal to nonmetal, metal to polyatomic ion, and metallic hydride. Those are the 3 types of bonds. Now, the next thing we have to talk about are the properties of ionic compounds. So, properties of ionic compounds. First of all, this is the easiest property. Remember, an ionic compound is a metal to nonmetal, metal to polyatomic ion, or metallic hydride. So the first property of an ionic compound is this: if it doesn't have a metal in it, it's not an ionic compound. No metal, no ionic compound. And there's only like one exception to that rule. So, if it doesn't have a metal in it, it's not an ionic compound. One exception that you have to know is this one. If the compound contains ammonium, it's considered an ionic compound. So we'll do one. Let's do ammonium nitrate. Ammonium nitrate. Now remember, ammonium is a polyatomic ion. And look, this ends in 8, so that must be a polyatomic ion too. So ammonium nitrate, that's an ionic compound even though there's no metal in front. So let's put this together. Ammonium nitrate. Ammonium is this, NH4 plus. Nitrate is this, NO3 minus. That is ammonium nitrate. That's an ionic bond. But look, we have a +1 and a -1. Do we have to crisscross? No, because they equal 0. So, first rule, remember, if it doesn't have a metal in it, it's not an ionic compound. Second property. The second property is all ionic compounds are crystalline substances, which means this. Watch. Example, Na plus Cl minus solid. So every single ionic compound is a crystalline solid. Every single one. They're not liquids, they're not gases. They're all crystalline solids, and the easiest way to think about an ionic compound is a salt. So, crystalline solid, NaClS. So, all ionic compounds are called solid salts. Every single one. All of them, solid salts. All right, that's number 2. Number 3. Number 3, salt, and it is a high melting point. So that is the next one. Salts have a high melting point. Now, the next one, the next property is the number 1 most important property of ionic compounds. So pay attention. Here we go. Put an asterisk here because it's so important. Solid ionic compounds. Such as Na plus Cl minus S. Remember, the S stands for solid. Solid ionic compounds. Solid ionic compounds can never conduct electricity. Ever, ever, ever. Never conduct electricity. Okay? Now watch. But when placed in water, now watch this. I'll put it down here. So, but when placed in water, Na plus Cl minus AQ. Remember, AQ means it's in water. So if you put an ionic compound, if you put a salt in water, Na plus Cl minus AQ, it will conduct electricity. Now here is the most important part. Why, if you put a salt in water, will it conduct electricity? Well, you know this. Metals conduct electricity because they have free electrons. They don't want their valence electrons, so they're free to move. So metals conduct because they got free electrons. Then why would putting salt in water make that solution conduct electricity? Not because of free electrons. It's due to free ions. The Na plus and the Cl minus break apart. So due to free ions. So solid ionic compounds don't conduct, but if you put them in water, they will conduct due to free ions, and there's one more way you can make an ionic compound conduct. So ionic compounds don't conduct in solid because they don't have any free ions. If you put them in water, it conducts because it's got free ions. If you melt it, like this, Na plus, Cl minus, L. L stands for liquid. If you melt it, it will conduct. So two ways ionic compounds conduct: if you put them in water or if you melt them. Okay, so this is the final property of ionic compounds. The larger the electronegativity difference between the metal and nonmetal, the stronger the bond. So here's one. Na plus Cl minus. So Na is a 0.7 electron. And Cl is 3.2. And so when you subtract the two, that gives you 2.5. All right, now let's try another ionic compound. Let's go with K plus and F minus. Well, you know that F minus is 4.0 and K is a 0.8. So the difference there is 3.2. So 2.5, 3.2. And it says the larger the electronegativity difference, the stronger the bond. So we know that Kf at 3.2 is a much stronger bond than NaCl. So that's the way to figure out if the ionic compound is strong or not. Subtract the electro differences. Okay? So, one last thing to write, and this video is done. Okay, so the final thing. When you subtract the electro differences, usually it should be 1.7 or higher. That's an ionic compound. There are some that are lower. That means that they're weak ionic compounds. But that's it. So that's all about ionic compounds. These two videos, that's it. The next video we're going to do is going to be bonds between two nonmetals. Okay?